This is MAT 5700 lecture number 39. Today we will finish the remaining sections I wanted to cover in chapter 6. These are section 6.4 and 6.5, but we'll go quite quickly actually. Okay, so let us get started. Okay, so 6.4 and 6.5, let's start with 6.4, are both about conditional distributions, so-called conditional distributions. In 6.4, we only consider the discrete case. So this is a distribution associated with a pair of random variables. Recall that if you have events A and B, the probability of A conditional to B was given by the probability of A intersect B, the overlap in the Venn diagram, divided by the probability of B. So now let us use this idea in the following way. So let X and Y be random variables on the same sample space. And we're considering the discrete case here. Okay, so I want to define a new probability mass function called, here's the funny notation for it. We put X conditional to Y. And the inputs here are X, and we put a bar between X and Y. So this is really strange notation. So let me just tell you what it is. It's very simple, actually. The notation is weirder than the definition. It's the probability that X equals X conditional to Y equals Y. So here X and the lowercase x's and y's are elements of the real numbers. And remember what this means. X equals X is an event. And this is notation for the event. It's the event. It consists of the set of all S in the sample space with the property that X of S equals X. So what this is, it's really just A above, and Y equals Y plays the role of B. So what this is it's the probability, it's actually the joint probability that X equals X and Y equals Y. That's what joint probability actually is. It's like an and divided by the probability that Y equals Y. Okay, so and we can think of this in the joint PMF notation as little pxy divided by the marginal probability distribution, probability mass function of y evaluated at y. So this is what it is. It's given by this formula. In fact, this is a PMF, right? So let me state that fact. This is a probability mass function. What do I mean by that? If I sum up, this is a probability mass function for x, actually, for the x variable. So what I mean by that, this is, we can sum up over all x's, p sub x conditional to y of lowercase x conditional to y. And what that is the sum, by definition, the definition in the green box, it's the sum of pxy. Here y is held fixed, so over p sub y of y, and we're summing up over all x's. And since the denominator here doesn't depend upon x, it comes out, and we get the sum over x of pxy. Now the sum over x of pxy of the joint distribution is the definition of the marginal distribution of y equal to 1. So that's why the fact is true, the fact holds. Okay, so that is that's the definition in the discrete case of the conditional probability mass function associated with X and Y. So let me do that. So this is called the conditional PMF of X conditional to Y. Okay. All right. So let me point out one also has an associated conditional cumulative distribution function for X. So what is that? So this would be the conditional CDF. And what it is its notation is given by the function f, capital F, X conditional to Y, and X, Y. And this is the same thing that the probability of X is less than or equal to X conditioning to Y equals Y. So this is by definition the sum over all A less than or equal to X of the probability, the conditional probability mass function of A conditioned to Y. Okay, so note, this is an important thing to note, what I'm going to write now. If X and Y are independent, notice that that the probability, the conditional probability mass function of X conditioned to Y is the same thing as the following. So remember, the numerator was the joint PMF of X and Y. And if it's X and Y are independent, then the numerator breaks up as this product, remember? Oh, and the denominator, by the definition, was P sub Y of Y. So you get cancellation occurring, and this becomes P sub X of X. In other words, the conditional distribution doesn't depend upon the random variable Y in this case. So this is an important point to make. Okay, so obvious. If we write in the case where X and Y are independent, in the independence case, this doesn't, the cumulative distribution function in the conditional case is the non-conditional one for X. So that's also true. Okay, so there you go. That's the definition. And so let me give you, I'm just going to give you one example and then we'll move to 6.5, okay? So in the one example, we have to compute something. Okay, so here we go. So, so let's, in the example, so let's roll a pair of fair dice. So, and let X be the value of the first, Y be the value of the second die. These are six-sided dice, and let Z be X plus Y, the sum of the dice. So now let's find the probability of Z conditional to Y, this function, okay? And maybe I'll specify what Y is here. So Y will be 5. We set the lowercase y equal to 5. So in other words, I want to calculate, let me use lowercase z here, PZ5. What does this mean? This means the probability that Z equals Z conditional to Y equals 5, remember. But you see, what does that mean? If the second die has value 5, and the sum of the dice is Z, that's exactly the same thing as the first I being equal to z minus 5. Okay, so what can you get here? Well, if z, remember, the value of x is a value of the dice, and that can only be 1, 2, 3, 4, 5, or 6. So this can only be non-zero if and only if z minus 5 is equal to 1 or 2 or 3 all the way up to 6. In other words, z equals 6, 7, 8, 9, 10, 11. So, and then the value of x being z minus 5, since it's a fair die, is 1/6 of the time. So the answer is this probability is given by 1/6 if z equals 6, 7, 8, 9, 10, or 11, and it's 0 in every other case. So this is like a uniform distribution. It's a discrete uniform distribution. Let me put that in quotes because I didn't really define that. Okay, that's the one example I want to do in the discrete case. I want to move over to the continuous case now. So I want to move over to section 6.5. 6.5 is conditional distributions, but we only consider them now in the continuous case. And it's all very analogous. Okay, so let x and y now x and y are continuous real variables, continuous random variables. And let's define now the conditional PMF. This is a probability mass function for the x variable. So it's going to be given by, and it's not a PMF, it's a PDF because we're in the continuous case. The conditional PDF of x conditioned to y. So what that means is we look at, this is the notation, it's just like in the discrete case, we just have an f instead of a p. The definition is f of x, y divided by the marginal PDF for the variable y. So that's the definition, just like before in the discrete case. Okay, so and then we have also the we also have the conditional CDF of x conditioned to y of a number a y, and this is the integral from minus infinity to a of fx. That's not an a here, it's an x. Y dx. We're summing up. Summing up is integrating in the continuous case. Okay, so that's great. Okay, so let me box that off too. And let me point out also that fx condition to y is a PDF. What do I mean by that? If I take the integral from minus infinity to plus infinity of that expression, fx condition to y of x, y dx, I integrate with respect to x, then remember that's integral from minus infinity to infinity, but using the definition of the joint PDF of x of the variables x and y divided by the marginal PDF of the variable y, and we're integrating with respect to x. And again, we can bring out of the integrand this function in the denominator because it has nothing to do with x, And if you do that, you're going to be left with 1 over f sub y of y times the integral from minus infinity to infinity of f of x y dx. But integrating the joint probability density function over the x variable gives you gives you the marginal p probability density function for the y variable. So this is going to be 1. So this checks out. This actually shows you we got a probability density function. Okay, cool. All right. So what's next? So let me talk about some other properties. Okay. Okay, so here's a property. So we saw that it was a probability density function. Now I want to point out that the second property I want to list is that f, x, and y are independent continuous random variables. Then what do we got? We got f, x condition to y is given by, well, let's take the definition again. But then the numerator in the independence case is f of the product of the marginal probability density functions, and then you get cancellation occurring here. So you're going to get f sub x of x. So now this doesn't depend upon the variable y, the random variable y. Okay, so let's. I'd like to do. Two examples now. Okay, so let's start off with the following example. I need to draw a line here. So the first example is, let's consider the following joint probability density function, which is given by 3/2 if x squared is less than or equal to y is less than or equal to 1. That's a region in the plane, and 0 is less than or equal to x is less than or equal to 1, and then it's 0 otherwise. Okay, so what does that look like? Well, if you graph that in the plane, that region, it's bounded by the curve y equals x squared, which is the parabola, and then y equals 1. It's this shaded region in yellow, where this is the parabola, y equals x squared, the green curve. That's okay. So you can check, and I won't do it, that this is really a joint probability mass function. And what I want to do is I want to compute, the problem is to compute what fx conditional to y is, the conditional probability density function. So remember, that is f of xy divided by f sub y of y. Now we know what f of xy is. That's given to us. We just have to compute the denominator of this fraction. So what is the denominator? Well, so let's figure out what that is. So f sub y of y is the integral from minus infinity to infinity of f of x y dx. That's the definition. Now, if you want to figure out what that is, for a given value of y on the y-axis, the only thing that matters is y should be going from 0 to 1, and we are going to integrate this for that given y, along this little segment. And what is that segment? That segment is given by x is between 0 and the point on the curve y equals x squared, which is the square root of y. So this is going to give me the integral from 0 to the square root of y of the value of fxy on that region, which is 3/2, and we're integrating with respect to x. And so we can compute that integral very easily, and you get 3/2 the square root of y. So what does that tell us? That tells us that fxy at the point xy is equal to, so you're going to get the numerator is the joint distribution, and on the region, this region that I've circled in yellow, it's going to be given by 3/2 over, oops, I don't want to make that yellow, I want to make it black. It's going to be given by 3/2 over the marginal distribution functions, which is 3/2 the square root of y, or in other words, the square root of y over y if we were in the region. So that's going to be x squared less than y less than 1, 0 less than x and less than 1, and then everywhere else it's going to be 0 otherwise. All right, so so there you go. Okay, great. So now what I'd like to do is one other problem. So the other problem I'd like to do is example 5b in the text. So this concerns the joint probability density function e to the minus x over y times e to the minus y, where x is between 0 and infinity, and 0 is less than equal to y is less than equal to infinity. That's the first quadrant in the plane, and 0 everywhere else. Now, you could actually check that this is really a good probability, joint probability density function. What we're supposed to do in this problem is find the probability that x is bigger than 1, conditioned to y being equal to y. Okay, so now what are x and y? What are the random variables x and y? These are random variables which have this associated, the displayed probability density, joint probability density function. So let's calculate the conditional probability density function first. So let's first consider calculating fxy, where x conditioned to y. So we know that that's fxy divided by the marginal density function for y. And the numerator, at least if you're in the first quadrant, the numerator is e to the minus x over y times e to the minus y. That's given to us. And what's the denominator? Well, we have to calculate the f sub y of y here. So what is f sub y of y? That's the integral from minus infinity to infinity of fxy dx. But that's the same thing, because if you're integrating out for x negative, there's nothing there. So it's the integral from 0 to infinity of e to the minus x over y times e to the minus y, and we're integrating with respect to x. And what do you get here? Well, that's the e to the minus, the antiderivative of that, you can check with respect to x, is e to the minus x over y with a negative sign in front of it. That's because if you differentiate this last thing I wrote with respect to x, you get the integrand. So that's cool. So what do we get? Oh, and we have to evaluate this from 0 to infinity. I have to correct myself. I didn't integrate this correctly. Let me erase this. So what's the antiderivative? That's given by e to the minus y. That's like a constant from the from the viewpoint of x, times minus y times minus e to the minus x over y. So that's what you get for the antiderivative. That does work. And then we're integrating from x equals 0 to x equals infinity. And what pops out of this is, it looks like to me, you're going to get y e to the minus y. You can check that yourself. So therefore, the f x condition to y is given by the density function. This density function is given by the numerator e to the minus x over y times e to the minus y over the denominator, which we just computed as y e to the minus y. And this cancellation that occurs, and you're left with e to the minus x over y divided by y. And here we're assuming that x and y are not negative. Okay, so now we go back to and solve the problem. We want to solve the original problem. So we have to calculate the probability. That x is bigger than 1, condition to y equals y. So what is that? Well, that's an integral from 1 to infinity. So of e to the minus of what we just calculated. Okay, so now this has an easy, the antiderivative of this is quite easy. This is minus e to the minus x over y evaluated from 1 to infinity. And if you evaluate it at infinity, you get 0. And if you evaluate it at 1, you get e to the minus negative e negative, oops, let me put that in correctly, negative e to the minus 1 over y. So, and that's given by e to the minus 1 over y, and that is the final answer. That's what we had to compute. And there you have it. That's all there is to do. We now know how to calculate these conditional distributions from the joint distribution. And that's all for chapter 6 that we're going to be covering. We are not covering the remaining sections of chapter 6. Those are optional sections. Okay.